that. It's, again, one thing to emphasize here is that people sometimes complain about regression-based tests because they tend to make you focus on the value of the test statistic instead of whether you're getting important differences in the estimates. But I would prefer a regression-based test that doesn't add a bunch of assumptions under the null to a test based on differences in the estimates if one is maintaining that one of the estimators is efficient under the null. Okay, so these regression-based tests these days can be made quite robust, completely robust to extra assumptions, and so that's more or less why I'm inserting these tests as we go along and basically showing, or at least describing how they can be implemented in a completely robust way. I have to say I was disappointed to see that Stata, I think even Stata 10, did not allow for a robust option in the fixed effects IV command. I don't know if anybody else has noticed that, but they do for fixed effects, but not for fixed effects IV. So I'm hoping that will change at some point in the future. Okay, so let's go back to this problem where we're not willing to entertain any kind of asymptotic bias, even though it might be a function of 1 over the number of time periods. So this comes back to the estimation under sequential exogeneity. And the weakest form of the assumption is stated 2 lines below equation 26, and that is just as a covariance assumption that the x's dated at the same time period as the u's, and then previous time periods are uncorrelated. This turns out to be enough technically to identify the parameters because it gives us some moment conditions we can use after we eliminate the unobserved effect. So because of the sequential nature of this assumption, the transformation that is convenient, or at least the one I'll talk about here, is differencing. There are some forward filtering transformations as well that Hayashi and Ariano and others have worked with, but I'll just focus on the simple differencing. Then we get a set of moment conditions as in 27, and then of course when we put the parameters back in, we can apply generalized method of moments. So under just the assumption of sequential exogeneity, what happens is we can use as instruments at time t the entire past history of the x's. Okay, so just having contemporaneous exogeneity isn't enough, but sequential exogeneity is, and in fact, once we impose that, we have, in principle, lots of extra instruments that we can use. And so if we set this up in a GMM problem, what happens is the matrix of instruments is this diagonal matrix. And what's happening is, of course, as you go further and further in time, the number of instruments you get is growing because you have more lags to use. And then allow GMM to essentially choose the most efficient combination of those instruments, and you're done, basically. There are some other simpler strategies, too, which involve just essentially differencing the equation as in 29, and then instead of doing a full GMM, just estimate a reduced form for each time period separately. This is a good way to get starting values, to get an initial estimator for the GMM weighting matrix, too. You need something in order to do that. And so if you get the fitted values from the change in the x's on the instruments, which I should have mentioned, of course, you have to lag them once you've taken changes for them to be valid instruments. So when you get those fitted values, that takes care of the problem that your instruments are growing with there are different numbers in each time periods because, of course, the fitted values are going to have the same dimension as x, and so you can now just use those as instruments in the pooled regression. And it's an inefficient estimator, but it's something you can do right away without having to go to full GMM. Of course, if we only use the sequential exogeneity restriction, this procedure often suffers from the so-called weak instrument problem, which Guido will be talking about later. And that's because if the x's are persistent and have so-called unit roots, then what we're doing is we're trying to use lagged values of the levels, right, which includes lagged changes, to predict the change in x from time period t minus 1 to t. Well, one case where there's no predictive power is when x is actually a random walk, because it really is just its last value plus a shock, and by definition that shock is uncorrelated with everything prior. And so this method, GMM doesn't really help in this case. It in fact just sort of serves to mask the problem. If you look at this method where you explicitly do the reduced form regressions, so in each time period you regress the changes on the x's up through the previous time period, you can see whether in fact there is significant correlation or not. And if there's not, you shouldn't probably go on, because what it means is that you really don't have usable instruments for this problem. Okay. So that certainly has been noticed in models with lag-dependent variables when the coefficient on the lag is close to 1, so that you have a unit root in the model itself, or close to 1. And it's also been noticed in applications such as production function estimation, where you have to difference something like the inputs, log of labor input or log of capital input, and then predict the difference, which is a growth rate, based on lags of those things. And often the lags of the things don't do a very good job. So more recently, people have been looking at other sorts of restrictions that one can impose. And one restriction would be in equation 30, which is much stronger than just saying the u's are uncorrelated with current and past x's. You can write it in two different ways. It says that u's are also uncorrelated with past y's, or that u's are also uncorrelated with past values of itself, okay, which imposes a no serial correlation assumption in the original model. So one would hope that if you're going to add an extra assumption like that you would get more out of it, and you certainly get more by way of moment conditions. Now, in the case of the dynamic, the simple Ar1 model, this has been looked at a lot, and I think people disagree on whether that model, by definition, really should have serially uncorrelated errors, but usually it's studied under that assumption. In which case, 30, adding the equation, the conditions 30 to the usual sequential exogeneity assumption really are no different. Okay? So there becomes more of an issue if you're estimating something like a production function where you don't have lagged output or anything like that. You're basically estimating a static production function. Should you be adding additional assumptions that say that the productivity shocks are serially uncorrelated? And I think many people would be uncomfortable making that sort of assumption, at least as a general identifying scheme. But if you make the assumption, then you get lots of extra moment conditions, and these have been looked at by An and Schmidt, for example, in the autoregressive case, and you can show that the moment conditions that it adds are given by equation 31. So interestingly, what equation 31 does is it adds a set of conditions that involve the levels of the equation as opposed to just the first differences. So before we first differenced and then used essentially lagged levels as instruments, 31 essentially considers the levels equation and then uses lag differences as instruments, with one small computational issue, and that is that the moment conditions are now nonlinear in the parameters beta. Okay. So this probably has been, empirically, this has been applied a lot less than just the standard estimator, which involves linear restrictions. I think partly because this is a lot harder, and partly computationally, a lot is an exaggeration. It's harder than just pulling up your canned program and doing it. And it also does impose these extra assumptions when you might not think that the model has the dynamics entirely complete. So others have looked at different conditions. Ariano and Bover suggested just saying, well, let's assume that the change in the x's is uncorrelated with the heterogeneity. Now, interestingly, this is very much in the spirit of that assumption that I talked about when the usual fixed effects estimator has robustness properties in the presence of random slopes. This just states it as a first difference condition instead of time demeaning. So the idea here is that if you think the x's are basically a random walk and the innovations are uncorrelated with the heterogeneity, but the initial condition might be correlated with the heterogeneity, then equation 32 is reasonable because it nets out the permanent component, if you will, from the x's. If you add this assumption, well, then it's to the sequential exogeneity assumption. Then you now get a set of linear moment restrictions in the parameters. So you get 33 in addition to the moment conditions that we already had. Now this, as it turns out, works pretty well. Okay, Blundell and co-authors have used this for exactly the problem of estimating production functions. And if you just use the initial sequential exogeneity restrictions, you get very imprecise estimates, which reflects this weak instrument problem. On the other hand, if you add these equations in 33, suddenly it ties things down much more tightly. Of course, you've added some assumptions. And just as I mentioned, when talking about the robustness of the fixed effects estimator, that's hardly for free. This assumption 32 is hardly for free. Okay, but if you are stuck with a case where you can't learn anything using the weakest set of assumptions, you might be willing to add something. In the case of the simple dynamic model, Blundell and Bond actually showed that this condition that was generally used by Ariano and Bond could be distilled into one extra assumption. Okay? And the extra assumption, I'll just go to the bottom line, is basically given by equation 39. So this random variable Ri0, if you assume that at time 0 the process is in its steady state plus some departure from that, so the steady state is Ci divided by 1 minus rho, and then plus this deviation from it, Ri0. Blundell and Bond basically showed that these extra moment conditions are the same as assuming that the deviation from the steady state is uncorrelated with the steady state. Okay. So, when you start imposing restrictions on steady states which are untestable, you might wonder whether you should continue. But as I said, there's no question that the additional moment restrictions that it adds, which are linear in the parameters, have been shown to help a lot, both in simulations and in empirical work. The more supportable conditions, which impose, in this Ar1 model, which impose these nonlinear restrictions, have been used very little, even though they are less restrictive. So in a sense, this probably has won out because of simplicity, at least in terms of the estimation. And it's fairly transparent in the Ar1 case. Okay, so of course, even though a lot of the theoretical work has been on the very simple Ar1 model, in practice you might want to estimate models that have both a lag-dependent variable and some other covariates, and an example of that would be in equation 40. Now, again, if the ZITs are actually changing over time, we might sensibly ask whether they are strictly exogenous. But it's fair to say that most of the time when we look at equation 40, our eye would be taken toward the lag-dependent variable as the first thing that we should be worrying about, because it clearly is not strictly exogenous in this equation. But whether the other covariates are or not is an empirical issue. The other one is not an empirical issue, okay, that it can't be strictly exogenous. So the methods that I just talked about can be applied to this case as well. The easiest thing is to difference and then to start counting moment conditions and decide which ones you're going to use. If the Z's are in fact assumed to be strictly exogenous, then it gives you lots of extra potential moment conditions, right? Because by definition of strict exogeneity, they are uncorrelated with all errors in all time periods. So in principle, you could add just a ton of moment conditions. In practice, I think, in fact, the Ar1 Bond approach generally would just use the changes in the ZITs as instruments for themselves, okay, instead of trying to add on these extra orthogonality conditions. There's an example that's covered in a bit more detail in the notes, just to see what happens in a simple example. They are data on airline routes in the United States for a 4-year period, 1997 to 2000. There's not that much information, except there is a concentration ratio for the routes there. And so these estimates that are reported at the bottom of the slide they're actually the estimates on the lag-dependent variable, even though one might be interested in the estimates on the concentration ratio as well. The dependent variable is the log of the airfare between the two points. With 4 time periods and a lag-dependent variable, you difference once, and then you have 2 time periods with which to work with. And you can see that clearly doing OLS on the first differences when you have a lag-dependent variable is shown. This example pretty much shows that's a bad idea. You get a negative estimate. If you implement that IV procedure that I mentioned, where you regress the change in the lag-dependent variable on changes t-2 or earlier, you get a more sensible estimate. And if you implement the Ar1 Bond GMM estimator, which essentially uses the efficient weighting matrix, you get a higher estimate and a lower standard error. So that's, of course, what you would hope from a procedure that is supposed to be more efficient. You can look in the notes for what happens to the coefficient on the concentration ratio, the route concentration ratio. Again, in that case, you do get a more precise estimate using the full GMM procedure. Okay, there is something interesting that happens with the large sample properties. It wouldn't be applicable in the example I just talked about because it has to do with when the number of time periods is getting large with N, and Arellano and Alvarez show that the GMM estimator that accounts for the particular structure of serial correlation that's induced by the first differencing does have some desirable properties as the number of time periods grows along with the cross-sectional sample size. Okay, the last topic I'm going to talk about is analyzing so-called pseudo-panel data sets, which are constructed from pooled cross-sections. And I should say, in looking through the recent literature, it seems that there are really only a couple of estimators being used, but they're analyzed from every possible angle you can imagine. So as I find in these cases, it's never a bad idea to go back to the original source, which in this case is a paper by Angus Deaton in 1985. And there I think he lays out the problem pretty clearly. The idea is we don't observe a panel data set on individuals for some well-defined population where the assumption is there's stability in this population as we march through time. but we can collect pretty good data set on independent cross-sections, so at each time period, a new random sample is taken. And it would be a fluke if somebody showed up in the sample more than once, and even if they did, you wouldn't be able to use that information in any useful way. So what is the setup? Well, the idea is, at least as stated by Deaton, is can we identify the population parameters in this model at the individual level using data that are on individuals but not on the same individuals as we move through time. Okay. It's a little surprising what comes out, I think, or at least I was surprised when I finally forced myself to go through this. So the model is stated in 42, and for some reason I've used F instead of C as the so-called unobserved effect or fixed effect, and I haven't put I subscripts on 42 because I want us to think of this as a population representing a population of the same group of individuals as we move through time. Okay. Because the eta t's are unrestricted time intercepts, then we're just going to assume that the expected value of F is just 0, and then we'll assume that all the x's have time variation because there's going to be a fixed effects type transformation is going to show up. Now, beta, of course, doesn't have perhaps too much of an interpretation in this model generally, although if we impose the contemporaneous exogeneity assumption down in equation 43, it certainly does, because now this again takes us back to this first equation that I wrote down, which is that ideally what we would do is estimate the partial effects of these x's on the average value of y, holding this heterogeneity fixed. Okay. Interestingly, in the pseudo panel literature, this assumption isn't used except for one thing, and that is what it implies about the relationship between the idiosyncratic errors and the heterogeneity, which is equation 44. Okay, so again, this is pretty much, this is just taking from Deaton's original setup. The way to think about this, I think, is that when you add on this heterogeneity, it's some aggregate of everything that affects the response variable that you can't control for but is constant across time. And so anything that's constant across time should have a zero conditional mean when you condition on the errors as well. And so if you let G is going to denote group designation or cohort, which is what the pseudo panels are based on, putting individuals into cohorts often based on birth year or something like that, then the way to view 44 is that it's going to imply that the mean of the individual specific effects is also conditional on group membership is 0. Remember, we're taking out aggregate time effects already in the underlying model. So, as I said, the implication of this is now if we have a random sample at each time period, then the implication is given in 45 that the idiosyncratic shocks are uncorrelated or mean independent, more precisely, of cohort or group designation. So the idea is to divide the population up into cohorts. Again, year of birth is a common one to use, and then to see how those cohorts, using the cohort data over time, can be used to identify the parameters in the underlying model. So if we use that, then we get this equation 46, which is really Deaton's starting point. That if you believe this underlying individual specific model, then there's a relationship between the cohort means of the response variable, the cohort means of the covariates, and of course that has a time component as well because we're observing different samples in different time periods. Moffat also basically starts from this equation where, in fact, xt contains a lag-dependent variable. Okay, as it turns out, the motivation of how to estimate beta is not really dependent on whether xt contains a lag-dependent variable. Okay. So if we just define now all of the population means, which, so the unobserved effect has a mean for each group, which is called alpha sub g. Then there are the means, the cohort means for the y's in each time period, so those are mu, y, gt, and the cohort means for the x's. Then this equation, 46, can be written like a regression equation, but it's in the population means as opposed to real data, at least so far. So the interesting thing about this equation is that it looks like a panel data model, right? It is, in a sense. It's in terms of population means. So if we have 10 groups defined by cohorts and 10 time periods, then equation 48 is basically for a 10 by 10 panel data set. Now, I said that this talk was only going to focus on cases where we have a large cross-section and a short number of time periods, at least for the most part. Usually that's violated by this kind of setup. But also, there's nothing about data here yet. Okay, so the question is, how do you turn this equation 48 into something that is estimable based on data? Well, in fact, what people did, actually what Deaton did, was then to plug in the sample averages for each of these and then treat it as a panel and then study the properties as G gets large. By the way, before I talk about that, there's something suspicious about this equation 48. It's derived without assuming any exogeneity assumptions at all on the x's. Okay? The only assumption it used was that the means, the idiosyncratic means conditional on cohort, are 0 after you take out the aggregate time effects. Okay? This should make us a little suspicious, I think, because I just went through what would happen with individual data if we have lag-dependent variable or other variables that are not exogenous. And contemporaneous exogeneity wasn't even enough in those cases to consistently estimate the parameters. But now we have an equation that looks like you can estimate these parameters basically without any assumption on the x's at all. And you see this, in the recent work, this is actually highlighted as a good thing, and it is a good thing, but then the question is, what's the source of the identification here, right? So how can you get away with this when you can't get away with it on individual level data? Well, the source of the identification is that you can't have any cohort/time period effects in the individual level model. So if there are effects that depend on cohort and time interacted, and they should have been in the original model to begin with, then that assumption on the error term that I made is no longer going to be true. Okay, so it's kind of an interesting trade-off between assuming exogeneity assumptions about your x's, which you pretty much have to do in the, or at least in some instruments in the individual level case, and here basically making exclusion restrictions on the individual level model. And that actually shows up in some common estimation strategies, which are based on, for example, equation 49. So when you look at this, let me go back up. Again, you look at this equation 48, and what does it look like? It looks like it has aggregate time effects. It has group effects alpha g. It has some covariates, which are the mu x g sub t. And we're trying to learn about beta. Well, that looks like a standard linear panel data model, and in fact, in the population, of course, if you do the usual time demeaning and subtracting and taking out the aggregate effects, you get, well, this isn't an estimator. This is a representation of the population parameters. So again, 49 is still a population equation. That is one way you can represent beta just in terms of the means of the covariates and the means of y's, where we've taken out those other aggregate effects and group effects. So in fact, if you look at equation 49, you would say, well, how would you estimate beta? Well, let's get the cohort or group time period means for each GT pair and plug them in, and that becomes an estimate of beta. It's a standard method of moments estimator where you have a population vector that you don't know in terms of some moments that you don't know but can estimate, and away you go. And in fact, in most of these applications, you do have a fair number of observations within each cell, because the idea is you hope to be able to get a big random sample from each time period. You're putting each unit or person into cohorts, but they're not really small cohorts so that you have 2 people and then a huge number of cohorts. That can be done, but often it's just a handful of cohorts and you have a lot of people per cohort. So you can estimate those means fairly precisely. Okay, this then becomes a not quite standard, but fairly standard problem in minimum distance estimation, where you view the sampling error as coming through estimating these population means. Now, the recent work on this has actually not taken this approach. It views the sampling, it typically does large G asymptotics and then just kind of tacks on an error term and then treats it as a fairly standard fixed effects model. But if you take Deaton's starting point, then it looks to me like this is clearly the intended way to go. As it turns out, that estimator, using 49 as the basis for estimation, you might not be surprised to learn is inefficient, because it seems that something about the cohort, the cell sizes, as well as the variability within cells should play some role if you're going to efficiently estimate, and in fact, not surprisingly, it does. So, as I already basically gave you this discussion of why it is we're able to do this, and the point is that we're excluding group time or cohort time effects from the structural model, yet at the same time we have to have the covariates themselves have some variation within group time structure. If the covariates, if you can write them, if you look at the second bullet on the slide, I did have a laser pointer here, but too late to use it now. There. If you look at that representation, if that's the way you think the x's essentially evolve over time and group, then clearly that formula that I wrote down is not going to be well defined. And again, this is all in the population. This doesn't have anything to do with data yet. So 49 doesn't exist because there's no variation in those variables with 2 dots over them. If all the variation in the x's can be explained by 2 additive effects, a time effect and a group effect. So that's the identifying restriction. And of course, if we had individual level data, we could allow group time, we could allow cohort time interactions. And so the fact that we're not doing that is basically where we're getting the identification from. Okay. So I mentioned that, so people have applied this so-called fixed effects estimate to the sample averages, and that turns out to be an inefficient minimum distance estimator. So the question is, how can one get the efficient minimum distance estimator? And actually, if you look at this problem, might as well use this now, the moment restrictions that it imposes has this form, where the thetas are the parameters that we want to estimate, which actually are beta, the time effects, and the group effects. We don't know what those are. Those are to be estimated with the data. The pi's, on the other hand, these are all of the means within group cohort, dependent variable, independent variable. So it's actually a fairly big vector. And you can write the restrictions like this. Now, this isn't the standard separable minimum distance problem where you have essentially the thetas being pulled out from this and equaling some function of the pi's. But, of course, you can work it through. And when I saw this and wondered if somebody had worked it through, I emailed Gary Chamberlain, and within a half an hour, he sent me some lecture notes where he had worked exactly this problem through with the efficient weighting matrix and what the asymptotic variance is, it turns out in this case it's easy because for a given value of pi, the restrictions are linear in the parameters of interest. So this does have a closed form solution. It should, because I already showed you the so-called fixed effects estimator can be, or I asserted it could be derived in this form. So when you work it through, you get something which is not at all surprising, that the efficient minimum distance estimator looks like a weighted least squares estimator. But remember, the asymptotics here is done not off of the dimension of the parameter, the group sizes or the number of time periods. It's being done off the sizes of the cells. So you can't derive the properties of this estimator as if it's really a weighted least squares estimator. You have to derive the properties as if it's a minimum distance estimator. And the way you get the efficient weights, if you will, is also not surprising. Is you want to give you want to give cells with relatively more observations more weight, and you want to give cells with relatively less variation in the regression residuals more weight as well. Okay, so to get the efficient estimator, you run the regressions within each group cohort, and you estimate the residual variances that way. So you actually have to go back to, the efficient estimator requires you to go back to the individual level data more than just computing the averages on y and x. As I said, if you want an inefficient estimator, then you can use this the so-called fixed effects one. But of course, its variance matrix is more complicated as well. So as I said, so there's some actually pretty recent literature on this and they all more or less come up with the same estimator, although not this efficient version of the minimum distance estimator. But again, the asymptotics is done in different ways. So let me just spend the last couple of minutes discussing the Deaton approach to this problem, except with the only exception that the sampling is assumed to be large cell sizes without trying to do the fiction that somehow the number of cohorts is getting large. Because, as I said, if you believe the identifying restrictions, then it changes with very little modification if you have lag-dependent variables. The only difference now is that if, as in equation 52, you have y on the right-hand side, you really don't have as many moments to estimate as you originally thought you did, because one of the moments is from a previous time period. So it's very easy to adjust the set of moment restrictions so that you don't get this degeneracy from basically estimating the same moments a couple of times. The other thing that's interesting about this is that you can extend this to fairly common extensions when you have individual level data. So if you wanted to if you wanted to look at the so-called random trend model that, as I said, has been used more and more, especially with more than a few time periods, then all that does to the moment conditions is add another term, which of course is a linear time trend. Now you have more parameters to estimate, but remember, you have a huge number of hopefully of observations and moment conditions to do that. And then again, I mentioned these models with time-varying factor loads, which would be in 55, and then you would get the moment conditions in 56. So again, there are more parameters added, and one might ask whether there's really sufficient variation in these moments across cohort and time period to be able to get precise estimates. I think the answer is generally no, but it is the method that is implied by this framework. As a comment, I haven't seen what I would call a completely honest simulation of these methods that has aggregate time effects, allows for group effects, and then generates the data in a way that doesn't rig the results so that it's going to work well. So I think this is still waiting for a fairly honest evaluation. So the last thing that I'll leave you with, I know I'm supposed to be answering questions and not asking them, but just to show you that maybe somebody who thinks about these problems a little differently should weigh in. Surely, in many of these cases, we're willing to assume at the individual level that some of the x's are exogenous in the very weak sense that they're uncorrelated with the idiosyncratic errors. The methods that have been used up to now in this literature don't use those assumptions at all, okay, which is, again, so you're trading off these different identifying restrictions. But if you're willing to make some assumption that you have some set of z's that are exogenous, it seems like you should be able to use that information. And one way would be to use as an equation 57, where you're just basically saying that this vector of z's is exogenous in the sense that they're uncorrelated with the idiosyncratic errors at time t. If you look at that equation, potentially there are a bunch of extra moment conditions there that should help to estimate beta. But the question is what you do with the very last term, as it turns out, because that's the one you need restrictions on to do this. So I will stop there, and I'm afraid right 1 minute over or something. But if there are any questions, I'm certainly happy to field a couple. Yes?
Can you talk a little bit about selecting the optimal group size? So a lot of it depends on having enough observations in each group times cell. So if you have really small groups, then it's almost similar to having individual level data. But if you have larger groups, there are probably some trade-offs. I was wondering if you could talk about those trade-offs and how you select the right.
Yeah, I don't think there's a lot of evidence on that, actually. Clearly, there is some trade-off there because, yes, if you do choose a large number of groups, then it makes much more sense to treat it as if the resulting model is a panel data model. And then what usually is done is the sample means are viewed as having measurement error in them, and then you try to come up with a way to solve that measurement error. But the solution that's been offered in those cases basically is to use cohort time dummy variables as instrumental variables. And that leads exactly back to that inefficient fixed effects estimate that I wrote down. So I don't know generally how one does that. Clearly, if you want to treat this in a framework where there's a clear answer to the efficiency question, is what's the most efficient way to use this structure, then that's arguing for larger group cell sizes. But of course, the more you do that, the less variation you're going to have in those cells. So I unfortunately, I think that's kind of an open question. And part of that could be answered with a simulation study that, again, allows for all the features that are evident in empirical work.